So the form that this is in right now is, it's hard to look at that and say, okay, did I do a quotient rule or something? Is that how it ended up looking like that? That's a difficult thing to try to anticipate, okay? But what I can do is I recognize that both of those pieces are divided by an x to the 1/2. So I could rewrite this problem as a definite integral from 3 to 8 of 10x to the 1.5 power plus 3x to the negative 0.5 power. And so now if I'm asking myself the question, what do I take the derivative of to get a 10x to the 1.5? We'll have to think a little bit. But this is a power function, so my power rule probably came into play here, and it means that that 1.5 used to be a 2.5. And when I took the derivative, the 2.5 came down. And so if I just took the derivative of x to the 2.5, it would be 2.5x to the 1.5. And the power's good, but the 2.5 is not big enough. It actually would need to have a 4 out in front of here. So the 4 times the 2.5 would make the 10. So the derivative of 4x to the 2.5 is 10x to the 1.5. Remember, the process here is I'm trying to find this capital F, which is an antiderivative of what we have circled in blue. And so I just figured out that the first part of it was a 4x to the 2.5. Okay, because the derivative of that will give me the 10x to the 1.5. The second part here, if the x is now to the negative 0.5, then it must have been to the positive 0.5 before, so that when I subtracted the 1 from it, I got the negative 0.5. But if I just took the derivative of this green one as it is, it would give me a 0.5x to the negative 0.5. And so I need a number out in front of there that when the 0.5 comes down and multiplies, it gives me a 3, and that number should be a 6. So the derivative of 6x to the 0.5 is 3x to the negative 0.5. So an antiderivative of 10x squared plus 3 over the square root of x is 4x to the 2.5 plus 6x to the 0.5. Okay, new on this. Okay, so in a little bit more detail, looking at the 10x to the 1.5, figuring out that it must have been a 2.5 before, so that when I subtracted 1 from that, I got a 1.5. And so I could say the only way that I'm going to get this 10x to the 1.5 is if I had some number times x to the 2.5. If I take the derivative of this, I'm going to get 2.5 times a times x to the 1.5. Okay? So if I call this capital F of x so far, then the capital F prime of x would look like that. Okay? But this 2.5a in my original problem was a 10. So I need 2.5a to equal 10. And if I divide both sides by 2.5, I get that the a was not 10. The a is 4. 10 divided by 2.5 is 4, and that's where this 4 comes from. So similarly on the other one, let me shrink this down a little bit so it's not taking up quite so much space. We had on the other one, we reasoned that it had to be some number times x to the 0.5, and if I take the derivative of that, I get 0.5 times b times x to the negative 0.5, and the x to the negative 0.5, that matches what I needed there. Okay. But this number out in front, that needed to equal 3. So my 0.5 times b had to equal 3, and if I divide both sides by 0.5, I get that the b must be 6. Okay? And so that's the 6 right there. Hopefully that helped out a little bit more for the people that weren't quite seeing it yet. So that is my capital F of x, and the thing that we're using here, remember, said that this definite integral from a to b of f of x dx was going to be equal to capital F of b minus capital F of a, where capital F is an antiderivative of lowercase f. So we've just found an antiderivative. There are an infinite number of antiderivatives, but the only difference is that they would be plus some constant, right? And what we discovered was that we can use any antiderivative, so why not use the one where the constant is 0? That's less stuff to write. It's not that it would be difficult with any other number added on there, because we'd just end up having that number, and then in the next thing we'd subtract the number off and they'd cancel each other out anyway. Okay? So the way that we would normally write this in the process is we would say, all right, I've come up with the antiderivative, which is 4x to the 2.5. I can write better than that. 4x to the 2.5 plus 6x to the 0.5. And the notation we typically use is we'll put a vertical bar, which means I'm going to evaluate. And I'm going to evaluate this from a to b from 3 to 8, where the 3 is the a, the 8 is the b. And so that means I'm going to, let me color code some things here. Make that the 8 and the 3. So I'm going to do 4 times, that's going to be 8 to the 2.5 plus 6 times 8 to the 0.5. So there is F, capital F of B minus capital F of A. So that's going to be 4 times 3 to the 2.5 plus 6 times 3 to the 0.5. And I need to make sure I put that in parentheses so I remember that that subtraction distributes through there. Okay. These are not numbers that are going to work out nice. 8 and 3 do not have nice square roots. So I'm going to have to type all this into my calculator to come up with an answer. Okay. Now, how do I know if I did it right? Well, at this point, you have some technology tools that also could have done this for you. They could have given you an estimate. So if you went into Desmos, or if you used your calculator program, or used your graphing calculator with some of the built-in estimation tools that are in there, then you could check the answer that you do this way against that and verify, yeah, I was doing things right, or no, it didn't work out right, and I have to go figure out what I did wrong. All right, so in this one, same kind of process. It's probably going to take us a little bit more work going along the lines here, though. Okay? Because if we're going to make this an obvious thing to see the antiderivative of, we're going to have to make it look like one big polynomial. which means I'm going to have to expand that x to the ninth plus 10 to the fourth power. Fortunately, I remember everything there is to remember about Pascal's triangles. All right, so 1, 1, 1, 1, 2, 1, there's the squareds. 1, 3, 3, 1, there's cubed, 1, 4, 6, 4, 1. Those are the coefficients that I'm going to need. So I'm going to do just this part, and then I'll distribute a 9x to the 8th through it. So I'm going to have 1 x to the 9th to the 4th, which is x to the 36th. So I got 1x to the 36th times 10 to the 0 power. Okay. Plus my next coefficient is the 4. I'll try to color code what I'm doing here as well. So that's going to be x to the 36th, the 4 from the Pascal's triangle, the x to the 9th cubed, which is x to the 27th, and the 10 to the first power, plus 6 from Pascal's triangle. The x to the 9th squared is x to the 18th, and the 10 is now going to get squared, so that's 100, plus the 4, x to the 9th to the first power is just x to the 9th. 10 cubed is 1,000, plus 1, x to the 9th to the 0 power, so none of those, times 10 to the 4th power. Okay. So that's x to the 9th plus 10 to the 4th. And I'm going to distribute a 9x to the 8th through that. Okay. So that's going to be a 9 now x to the 44th power, plus 9 times 4 is 36, x to the 35th power, 360, sorry, I forgot about my 10, 360 x to the 35th power, plus 9 times 6 is 54 with a couple of zeros, and x to the 26th power, plus a 36 with 3 zeros, x to the 17th power, plus 9 with 1, 2, 3, 4 zeros, x to the 8th. So I changed my problem into this. They didn't give me any numbers on there, did they? Is that the problem with this? This was not a definite integral problem. Okay, so this is what we're going to do with this one. I didn't notice that I hadn't hit definite integral problems on these last 3. Okay. So what it's actually looking for is just what that capital F of x function would be. Okay, so we're saving a step, and all it's looking for is what would the capital F of x be. Okay. Well, this x to the 44th used to be an x to the 45th. Right? And so when I took the derivative of that, the 45 came down and multiplied by something to give me a 9. I think that means it would have had to have been a 9 over 45. So if I do 9 over 45 times 45, the 45 over 45 makes a 1, and I'm just left with a 9. Okay. I'm going to pause. So on one hand, it didn't have the numbers on here, so we're not going to be able to get a number as an answer, but that also means that we're not going to have to plug numbers into all of these x's that we've got here. Okay. So the next piece was an x to, used to be an x to the 36th, right? But the 36 came down. And so it would have been like a 360 divided by 36, which is just a 10. So that worked out pretty nice. This used to be an x to the 27th, and when I take the derivative of that, that comes down, and I think 5,400 divided by 27 might give me a decent number too. That's just 200. Plus, this was something x to the 18th. Let's see if our luck should hold out on that one. 36,000 divided by 18 is 2,000. X to the 18th. Plus, this was an x to the 9th, and dividing that by 9 will leave me a 10,000 x to the 9th. Okay. So this is an antiderivative of x to the 9th plus 10 to the 4th, x to the 9th plus 10 quantity to the 4th power times 9x to the 8th. And 9 over 45, of course, reduces as well. I could have written that as just a 1/5. So, rewriting these things with probably negatives and fractions, right, is what's going to give us the insight onto this. This is another one that didn't have the numbers on here. So it's just asking us to find what the antiderivative is, or an antiderivative of this. You notice in the answer it puts a plus c at the end to say that it could have been any of these. Any constant you add on there would also work. Okay. So we'll rewrite this as 16x to the negative 6 plus 7x to the 1/3. And so if we want the capital F again, using the power rule, this is where we have to be a little bit careful, because if I ended up with an x to the negative 6, by subtracting 1 from the power, then it must have been an x to the negative 5th to begin with. So it would have been as an a times, we'll kind of work it out the longer way here, a times x to the negative 5th plus b times x to the, would have been 4/3. So when I take 1 off of each of these powers, I get the x to the negative 6 and the x to the 1/3. So if I then take the derivative of this, I'm going to get a negative 5a x to the negative 6 plus 4/3 b x to the 1/3. And I know that my negative 5a has to be 16. That means a is negative 16/5. And I know that my 4/3 b has to be the same thing as 7. So b would be 21/4. And so my answer, with those numbers filled in there, if the a is negative 16/5, the negative 5 is going to cancel. It's going to leave me, or Derivatives, negative 5a. Oh, the a, I'm putting my equal sign in the wrong spot. Right? This is my capital F that I'm looking for. My a is a negative 16 over 5, x to the negative fifth, plus the b, which is 21 over 4, x to the 4/3. Okay? And then the problem itself throws the plus c in at the end to indicate again that this is every antiderivative of 16 over x to the 6 plus 7 times the cube root of x. That will work for us here. This is the part that goes in the answer box. So let's take a look at problem 16. It wants to find the average value of the function on the interval without integrating, but by appealing to the geometry of the region between the graph and the x-axis. Okay, so our function is f of t equals 1 minus the square root of 1 minus t squared. And we're looking for the interval from -1 to 1. And they give us a graph. Graph looks like this. This is the bottom half of a circle shifted up 1 from the origin. Okay, so the center of the circle would have been there. Before the circle was down here, it was radius 1. And the bottom half would have been down here. But when we shift that up 1, then now it looks like this. And we're looking for the average value of that function. Remember, the average value is 1 over b minus a times the definite integral from a to b of f of x dx. Okay, or in this case, f of t dt, the variable doesn't really matter. All right, so the area that we are trying to find, this definite integral from a to b of f of x dx is this down here. Okay, and people on this problem frequently want to try to defer to the area of the circle, but what we actually need is this part that is outside of the circle. And we can get to that by saying, well, what we have here is a rectangle minus half a circle. A rectangle that is 2 units wide, and it is 1 unit tall, and we'll subtract half a circle of radius 1. So we've got 2. The circle of radius 1 has an area of pi, but we only want half of that circle. So that's like a 4 minus pi over 2. And that is the value of the green area, but we wanted the average value of the function. So we need to also multiply this by 1 over the width of the interval, which was 2. So we get 4 minus pi over 4 is the average value. As a number, just to make sure that it makes sense here, that is a 0.21. This would have been like a half, so it's a little less than a quarter. In here, this approximately 0.21. As the average value, meaning of course that if we made a rectangle of height 4 minus pi over 4 and width 2, that it would have the exact same area as the green area. All right, we see any other questions in there of interest? Couple other things before we run out of time here. How did we get pi over 2? Pi was the area of a circle of radius 1. So the whole circle I had is pi r squared, but we only were subtracting half a circle from it.